So now that you guys are experts on electric fields and you understand the forces that charged particles experience, we're getting ready to put that knowledge into practice and put into a context that you guys are familiar with, which is electrical circuits. Okay, so the objectives in the next few lessons is to begin understanding the relationship between electric circuits and voltage, current, and resistance, these three variables. If you change the voltage, how does that affect the current in a circuit? And if I change the resistance in a circuit, how does that affect the current or the voltage required for things to happen? Okay, so then this little picture here, you can see you can draw a circuit on paper with graphite pencil. Now, graphite is conductive, and you can even make a circuit on paper where if we connect this battery to the other side, we can light up the light. Okay, so this simple drawing is very similar to what is inside of your wall or inside of your Nintendo switches. Okay, it's a simple circuit where you have a battery, conductive wires, a resistor or a light bulb component that spends energy, and then that circuit can come back and complete the motion of charge. Okay, so we're going to play around with the variables of voltage, current, and resistance and learn how to draw these circuits over the next couple weeks. And then what we'll be able to do is understand how to even create some complicated circuits such as sensors or motors by the end of this. Okay, but before we get there, let's start with understanding what is voltage, because I know you've all come across the term volts in your life. Okay, if you plug the wrong voltage into a device, it breaks the device, and I'm sure that's happened to all of us here in Ghana. All right, so let's get going. What is a volt? Okay, so voltage is a unit of electrical potential. Okay, just like gravitational potential energy, stored energy. Okay, so a voltage is a unit of electrical potential or stored energy. And more importantly, the voltage is the amount of work required per unit charge to bring a charged object from an infinite distance to a specific place in an electric field. Whoa, that's a complicated definition. So a volt by itself is not energy. It's not the potential energy by itself. A volt is the ratio. It's the amount of energy, the amount of work that I'd have to do per unit charge, okay, per coulomb, to bring an object from, let's say, an infinite distance away, okay, really, really far away, to a specific place outside of another charged object. Okay, so if I'm infinite distance away, all right, how much force is there an infinite distance away? How much work would I have to do? Okay, so let's just remember a few things. Okay, so work is equal to force times distance. Okay, so if I'm out here and I have a positive charge, how much force is being experienced on that positive charge at an infinite distance away? Okay, so the force, as we remember, is K, Q1, Q2 over R squared. Okay, so K is going to be the Coulomb's constant, 8.99. Q1 is going to be this charged object over here. Q2 is the charge on that object, and R is the distance separating those objects squared. Okay, so if I'm an infinite distance away, infinity squared becomes a very, very large number. So we can say that an infinite distance away, my force is basically 0 newtons. Okay, and with that force, then, yeah, basically I wouldn't have to do any work whatsoever to move that charge around. But as I move this charge towards here, okay, now I'm getting to 100 meters. That's a lot smaller of a number. That force is going to start to get larger and larger and larger as we start to move that charged object there. So if I had a hand or a finger, okay, that's a bad drawing, okay, and I'm trying to push that object, that charged object with my pinky finger, I'm going to start to experience a force that's pushing me in the opposite direction. And as I get closer and closer and closer to that charged object, I'm going to have to put a lot more force into it in order to get that charged object over there. And remember, work is equal to the force that I applied times the distance that I'm moving. Okay, so all of a sudden, the amount of work that I'm going to be doing is increasing, and the joules that I'm doing is increasing. So a voltage is the amount of work that I had to do to bring that object to that place divided by the charge of that object. Okay, I'm not going to go into too much more detail, but for those of you that want to get ahead and get into grade 11 type stuff, okay? We can take a look at this formula over here. So I can take a look at this formula over here, and I can even calculate what the voltage would be over here. So what would that voltage be? Okay, so if I wanted to calculate the work that I'd have to do, force times R, okay, R would be that distance. Force times R, because force times infinity would be 0, but force times R would give me the total work that I'd have to do to bring that object to here, to that point. Force times R divided by charge 2 is going to be my voltage, okay? And if I look at this equation over here, I can rearrange it and I can calculate what the voltage is going to be. Voltage is equal to KQ1 over R, okay, where R is the distance separating this charged object and that point X, okay? So that would be the equation I would have to use. We're not going to use this year, but if you just were interested, how can you calculate? Ooh, that's interesting. Whoa, okay. How can you calculate the voltage at a specific point in an electric field over here? That voltage can be calculated by taking Coulomb's constant times the charge of the central object, Q1, divided by R, and that would tell me the voltage at any point away from that object. Okay, and remember, voltage is how much work I'd have to do to bring an object from a really far distance to that point divided by the charge of that object. Okay, and that would be stored, all that work that I would do to put that object there would be stored energy. Okay, and that energy can be used for something else. Okay, so here's just another diagram. Here, I'm just going to try to delete that box. Okay, here's another diagram where we're just going to try to understand the difference between high electrical potential and low electrical potential, or high voltage and low voltage. Okay, so if I'm an object at infinity and I'm brought to that point over there, let's call that voltage 1. Voltage 1 is a fixed distance away from that central charged object. Okay, so that's a fixed distance away. If I make a circle and I walk along that circle, I will be at the same voltage because I'm always a fixed distance away from that central charge. Okay, so that's voltage 1. I would have to do less work to go to voltage 1 than I would if I went to voltage 2. Voltage 2 is closer to that charge. I'd have to do more work. And if I walked around that circle, I would have the same voltage as voltage 2. Okay, so what we can see here is voltage 2 is a higher voltage than voltage 1. It has higher potential energy. Okay, and if I wanted to go from here to here, I'd have to jump a potential difference. I would have a potential difference going from this voltage to that voltage. And that potential difference would tell me how much work I would have to do. Okay, so for example, if I was at 10 volts at voltage 1, and this is 100 volts at voltage 2, if I'm going to walk from here to there, the potential difference is equal to 90 volts. Okay, so I would have to put in 90 joules of energy per coulomb of charge to move myself from voltage 1 to voltage 2. Okay, next thing. All right, so voltage in a battery. This is where we usually don't take a look at voltages around charges. What we're used to seeing at the house are batteries that have voltages written on them. Okay, so a 9-volt battery. Okay, what does that really mean? Well, in a 9-volt battery, a chemical reaction has moved the charges to one side or the other side in the battery. So 9 joules of energy has been used per unit charge to move and separate them on different sides. Okay, and that 9 joules is stored energy, and that energy can be used to move electrons. So if I would connect a wire from one side to the other side, now the electrons can flow through the wire and move to the other side and be attracted to the other positive charge. And that 9 joules per coulomb is used as energy that can be transformed into kinetic energy. Okay, so 9 joules per coulomb of energy. Okay, how much energy would an electron have? Okay, if I multiply by the charge of an electron, which is 1.6 times 10 to the minus 19 coulombs. All right, that would give me the total energy of an electron. Okay, the energy that an electron would have as a result of being given that potential. Okay, and then that energy of that electron could be transformed, into kinetic energy. So I would be able to calculate the velocity of that electron if I wanted to. And we'll do that in the next video. I'll go through a bunch of problems with that in the next video.